We've talked about some kinds of algorithms that we might describe as being divide and conquer. Um, where we have a problem and then we break it into smaller parts and solve those smaller parts recursively. And then once the smaller parts are solved, then putting everything back together as being a solution to the big problem. So for instance, what have we seen that might be divide and conquer? Maybe merge sort. Break the problem apart into smaller pieces, solve the smaller pieces, and then put those back together, right? Um, and so in those cases, we have subproblems that we create. Those subproblems are separate, so we solve each one of those subproblems and then put everything back together in some way. There are other situations where, well, let's go ahead. There are other situations where we have the subproblems not being independent. So subproblems share kind of subproblems. Right? So you have something that you need to solve here. So you have a big problem. You've broken this up, and these pieces share a common subproblem here. So what would we do if we were doing it in a divide and conquer approach? We would come to here, we would solve this one, then we would come here, we would solve this again, and then put it all back together. So we would have solved this subproblem twice, even though we didn't really need to solve it twice. So what we're going to talk about now is a different method that involves, well, by name, is called dynamic programming. In this context, programming doesn't really mean writing a program, but rather how we're keeping track of information. And so, I mean, we do write a program to implement this idea, but the word programming doesn't mean, anyway, okay. So what we're going to do is, rather than repeatedly solving those subproblems, we're going to solve those pieces once and record that information to keep track of it for future use. And then when we need it, we will write that down and have that answer. So for dynamic programming, we've got these ideas of we need to be able to describe the structure of an optimal solution. Right, so the first step is being able to say what the kind of answer we're looking for even looks like. We're usually going to use this kind of approach to solve like optimization problems. And an optimization problem, we're trying to find the best of something like we've been doing so far, try to find the best solution that fits a certain criteria. But there might not be the best solution, it just might be a best solution. So there might be multiple best ways to solve the particular problem. Right? There might be multiple ways to get from A to B as quickly as possible. Or there might be multiple ways to combine these different pieces to have the most value, or we'll see some other kind of scenarios next week that involve other ways of other optimization kinds of things. All right, so what we will do still involves this recursive aspect. And then rather than calculating from the top down, we will calculate these values these values bottom up, and that way we only calculate those pieces one time. If we only want the value, we stop here. If we want the process, like again, if we're finding a shortest path, if we just care about the length of the path, we stop here. Otherwise, we keep track of extra information along the way, and we construct an optimal solution from the information that we've calculated or stored. Okay, so this is very general sounding, but what's the idea? We still think about the problem like we would have thought about before in terms of, okay, there are subproblems that we need to solve. What do they look like? What do the pieces look like? How do we build a solution? But then rather than starting at the top and working our way down, we're going to start at the bottom and work our way up. And remember those pieces as we go. So in the solutions, the sub problems, if you need that answer again, you already have it calculated and recorded so that we can use it again. There's some ideas of what are called optimal substructure. So optimal substructure a problem has optimal substructure if a solution to the main problem also contains solutions to the subproblems. So let's look at an example rather than trying to be formal about this. Let's say we have a graph that's ABCD, and it looks like that. All right, and we want to find, we're just no weights involved, we just want to find the unweighted shortest path. And let's say we want to find the unweighted shortest path from A to C. When we said the unweighted shortest path, it's really an unweighted shortest path, because what? There are two shortest paths from A to C. What are they? We have A to B to C, and we have A to D to C. And those are the two shortest paths, so there are two solutions to this particular problem. Well, this solution to the unweighted shortest path from A to C contains this portion, which is the shortest path from A to B. It also contains this, which is the shortest path from B to C. And then the same thing for D on the other side. So this problem, unweighted shortest path, contains optimal substructure. Solving this problem for the whole thing contains in it answers for the subproblems that are also optimal. But let's look at unweighted longest simple path. From A to Z. So we're going to look for an unweighted longest simple path. What is a longest simple path from A to C? Simple path meaning not using edges again. Here's a longest simple path from A to C. Is this a solution for the problem for the longest simple path from A to B? No, because the longest simple path from A to B would look like that. So this problem has optimal substructure. This problem does not have optimal substructure. If a problem does have optimal substructure, then it means that it's a good candidate for a greedy algorithm or a good candidate for dynamic programming. If it does not have optimal substructure, then probably want to try to find a different way to solve it. You see how this contains solutions to the smaller problems inside it, but this one doesn't? Smaller problem is saying, what's the longest simple path from A to B? Well, it's definitely not just go straight from A to B. It's go around the other way. And this solution doesn't tell you that. It doesn't indicate that in any way. But this solution says, well, what's the shortest path from A to B? Well, it's part of the shortest path from A on to C. Another aspect of dynamic programming is if a problem has overlapping subproblems. So if we have overlapping subproblems and we have this optimal substructure, then what we want to be able to do is, as we solve the smaller problems, remember that, because the overlapping part means that you only have to solve that part one time. You can then save that and use it later for other parts of the problem. So again, we'll have some space issues because we have to remember some information. We have to remember those solutions, but often that will speed up the process because we don't have to calculate those answers again. So we do that trade-off of saying, okay, let's save it in a table somewhere, or save it in some format, so we can look up the answer when we need it, rather than trying to recalculate. So we make that choice of being able to look up the answer, and having the extra storage is better than having to recalculate that all over again, maybe possibly a bunch of times. Okay, so we're going to we're going to look at an algorithm that was designed, unlike Dijkstra's algorithm, for single source shortest path, so the shortest path from here to all those other places. We're going to look at a problem that is the all pairs shortest path. Okay, so for all pairs shortest path, we want to, our algorithm at the end will not just tell us the shortest path from A to F like we had in an earlier example. It will tell us the shortest paths between all the possible pairs of vertices. So you can think of it like a matrix of shortest paths. And in our case, this is going to be all pairs shortest paths on a directed graph, although if it's not directed, it still works. But we are going to be on a directed graph, and so the end results might not be symmetric, right? The distance from A to B might not be the same as the distance from B to A. In this particular algorithm, negative weights are okay. But negative cycles are not. Right, so we can't have something like, well, we can have something like that, but we can't have something like because in minimizing this, we would just keep going around the cycle, keep going around the cycle, keep going around. And so, but negative weights, a single negative edge, I mean, we can even have something, you can have something like that, and that's okay, because that's not a negative cycle. There's a cycle if you ignore the direction, but with the direction, once you get here, that's it. Or once you get here from there, that's it. So this is not a problem if we have direction. If we didn't have direction, that would be a problem. But this algorithm is really designed for use in a directed graph with maybe negative weights, maybe not, but definitely no negative cycles. It doesn't tell you whether there are negative cycles automatically, though. So some algorithms, if there are negative cycles, it will detect them and report that. But this algorithm won't automatically report that. Okay. So the algorithm that we're looking at is named after, again, two people, Floyd and Warshall. It's from 1962. Warshall came up with a theorem about matrices, and Floyd then used that in the development of the algorithm. And it all happened publication-wise in 1962. Floyd's paper is called Algorithm 97. So I don't know if it's his 97th algorithm or if it's a particular algorithm. I don't know the history on that part. So anyway, so the idea of this one, we've mentioned the runtime kinds of things. This turns out to be theta of the order cubed. And there are no elaborate data structures needed, so the constant that's hidden away in there is a small value. So this is a good algorithm for what it's for. All right? All right, so what we're going to look at is we're going to let G have vertices just 1, 2, up to some number n. And so even if they're labeled in some other way, we'll just think of them as being labeled numerically. And then we're going to consider a subset of those vertices, let's call it S, which is just 1, 2, up to some number k. So we're going to consider these subsets. We're going to change k. K will start small and work its way up. So for each pair of vertices, I and j, V, the vertex set, just 1 through n. We're going to consider all the paths from I to j whose intermediate vertices are in S. So we're only going to consider the paths from I to j that go through the subset that we're considering right now, where all of the intermediate vertices are in the ones from I to k. Now there might be other paths out there, but what's going to happen as this subset S gets bigger and bigger and bigger, eventually S is going to be everything. So eventually we're going to have all of the possible paths under consideration. Okay? Of all these paths, let's let path P be a minimum weight path amongst those. Okay, so we're going to set it up kind of in this way, and then we'll do an example specifically with actual numbers so you can see what's happening at each place. All right, now what's going to happen? We have vertex I. We have all of these vertices in S, and we have vertex J. I and J could potentially be in S. But from I, we're going to this set, and then all the other edges are between here, and then we go to J. So there's no other vertices involved in our path P. Now what can happen? Path P may or may not include that vertex K. So we're going to look at it in two situations, if it does and if it doesn't. All right, so what is path P doing? Path P is going from vertex I to vertex J, and the only vertices in between include things from here.
So it's not all of those vertices?
Not all of them, necessarily. It might be.
Okay.
But it's not necessarily all of them, but the only things that are there are things from here. It's not, we don't have some other vertex out here somewhere that's part of the path. All right, so we're only looking at the potential paths that go through, only through some or all of these vertices. Okay. This path P, that's a minimum weight path, which we don't know what it is yet, but if we had one, it would either include K or not. All right, so let's say that it does not include K. If it's not an intermediate vertex on path P, this is, I should have found a shorter way. All the intermediate vertices. Not earth-shaking. All the intermediate vertices came from the set 1 to K. If it doesn't include K, then everything came from 1 to K minus 1. So a solution from I to J, where everything comes from here, the shortest path there, is also a solution to the one that we were trying to solve right now, which is that subproblem. So if K is not on the path, then solving this problem solves that one. Right? It's not, I mean, It's a lot of words to say something that we could have, that we understand, right? It makes sense that if we're looking for answers that involve these numbers, and we know for sure it doesn't involve that one, then we know it involves these instead. So a solution to a smaller problem solves the problem that we were trying to solve at that point. All right, what if K is an intermediate vertex? Then what? Well, then let's break P up. Let's decompose path P into two parts. Let's decompose it in the part that's, remember, path P starts at I and goes to J. But now we know that it goes through K to get there. So let's break this up into the first part that goes to K and the second part that goes on to J. Now what do we know? All of this and all of this involve vertices from where?
Say it one more time.
The vertices in path P1 are from where?
Yes.
Well, the condensed version,
Oh, yeah.
right? The intermediate vertices are from here. Intermediate vertices from here are also from there, right? 1 to K minus 1, because we already took out the involvement of K in that issue. Does that make sense? We wouldn't come back to K again in here or in here. We wouldn't go from I, go through something to K, go through something and come back to K, and then go on to J, because we want a shortest path. What would we do? Leave that part out of it. Does that make sense?
I thought K was like the end.
K is just one of the vertices. It's labeled, they're labeled 1 through n, so it's just the vertex that has label K. But it might not be the end of anything. It's just one of those numbers. So if our path goes through this K, we might have gone through vertices 1, 2, and 5 over here. K might be 6, and over here we went through vertex 3 and 4 to get on to J.
So, we think about this wrong the whole time then, because we put K at the end. I thought it was just K was at the end where J was.
These are just a list of numbers. So
Right.
these are the labels of the vertices.
Okay.
If you change the labels of them,
They're the labels, but in no particular order.
well, these are in numerical order, but they're not in the order that you might run into them in the path.
Okay.
So the labels are in numerical order, but not necessarily the order that you run into them as you are going through the path.
Okay, I think I follow now.
So if we have just there are the labels, 1, 2, 3, and 4.
Mm-hmm.
They went here, then they go there, then here, then there, but
It could be
they're not in order in the path. So we don't want to, we're not adding any extra structure to the graph. This is just the labels that we're looking at.
In that case, K would be 4.
Well,
Or
it
it could
depends
be-
on which K we're looking at, because K will start and it will get bigger as we go through. N is 4, but we're going to start with K equals 0. Well, we'll start with K equals 1. Have a value that corresponds to what it means when K is 1. So we'll have K equals 1, and then K will be 2, K will be 3, and then eventually K will become 4.
Gotcha.
Okay, so what happens if K is one of the intermediate vertices? There's a part that would go from I to K, and a part of the path that would go from K to J. And there wouldn't be any cycle, because we wouldn't need to come back to K. If you ever came back to K, you could just take that part away and have a shorter path. But what happens with this part? This is where the optimal substructure comes into play again. This part is only going to contain vertices from here. And this part is only going to contain vertices from here as well. So if we can find the shortest path to here, and then find the shortest path from there, we can put those together to find the shortest path from I to J. Okay, let's do this with an example. Actually, first of all, let's write down some pseudocode for the algorithm. So pseudocode for the algorithm. Our first step is we're going to create a matrix W, which is our adjacency matrix, but with the weights. Right? So this is our directed adjacency matrix. With weights. N is the number of rows. All right, so that's going to correspond to the number of vertices. All right, now we're going to create some matrices. So D, I'll use this notation because I've seen it in more than one place. D is kind of raised to a power, but the power we'll put it in parentheses here. That's W. So now we're going to have 3 inner loops here. And what we're going to do is we're going to get the entry for row column ij in K is going to be the minimum of the corresponding entry in matrix K minus 1, or the sum of I to K and K to J in the matrix before. And then we will return the final matrix. Don't stress this too much. What is this saying? It's saying that the shortest path from I to J at a particular point is either the shortest path that doesn't include vertex K, or it's the length of the path from I to K and then the path from K onto J. So this is saying that this shortest path is, when you did include the intermediate, is just the sum of the lengths of the two paths. this shortest path plus this shortest path. So that's all this says. All right, but let's do it again with an application with a particular numbers, an actual picture, so that we can see how this carries out. Seems to be okay. The clock's right now, right?
Mm-hmm.
Okay. Okay, so let's see here. We have a
You just had to make it ugly.
all right, so we have some negative weights. Those are okay. We have direction on all of our edges. Negative weights are okay, but we don't have any negative cycles. We can check that ourselves and see that we don't have that. Okay, so our starting matrix, our adjacency matrix, I'm going to go ahead and call it D0. Going to write these down. Labeled so we can keep track. And what are we going? We're going from here to here. All right, so what happens, first of all, we know that all the way down the diagonal we have no loops. So these have zeros. 1 to 2 has weight 3. 1 to 3 has weight 8. What about 1 to 4 and 1 to 5? You can't get there. Those are infinite. Just like we did with Dijkstra's algorithm, saying if you can't get there yet, if you don't have the length there yet, it's infinity.
So if it's negative, you also put infinity?
No, actually I put that the wrong direction. Not that one. That one's -4. No,
That'd be big.
I looked at that arrow and thought, oh, they both point at 1. No, this one points at 5. That's a -4. This one is the infinite one, right? Because it points from 4 to 1. You can't get straight from 1 to 4. All right, let's look at 2. 2 to 1? Infinity. 2 to 3. 2 to 4 is 1. And 2 to 5 is 7. 3 to 1. 3 to 2 is 4. So here is our starting matrix, D0, and it gives shortest paths I to j with no intermediate vertices, right? These are the shortest paths that just go from that vertex straight to the other one. No vertices in the middle. Okay, now we're going to look at D1. This is going to look at all the paths that go through vertex, whose intermediate vertices are in this set. Right, so K is 1 at this point. But what still happens? We either include K or we don't. If we don't include K, what do we have? That means that this is our best answer so far. If we do include going through there, then we might sometimes get a better answer. Okay, so what happens? Well, the top row going from 1 to anywhere, that doesn't change because we already are going through vertex 1, right? I was K at that point. All right, let's see what happens in terms of the other situation. So what are we going to do? We want to see to go from 2 to 1, and we're allowed to go through vertex 1 if we want to. Well, again, got these up too far. It's not worth it. Going from 2 to 1 and being allowed to go through 1 doesn't help us any. So we get the same value that we had in the old case. Going from 2 to 2, these values we don't have any negative cycles, so those can never go down. If we had negative cycles, those zeros could become smaller, right? All right. What about from 2 to 3? Well, it turns out in this particular case, let's jump down to row 4 because this is the only one that has any changes in this particular case. All right. So going from 4 to 1 and being allowed to go through 1 still gives us a 2. Now we're going to go from 4 to 2. 4 to 2 over here is infinity. But we're going to cycle through all of the values and we're going to say, okay, well, I can go to 4 to 2 by going through 1. So let's look up the 4, 1 entry over here. The 4, 1 entry in the previous graph, right? We're saying I'm going I is 4, J is 2, K is 1. So I'm looking at going from 4 to 1 in one move, and then I'm going to look at going from 1 to 2 in one move. So with no intermediate vertices. So 4 to 1 is 2, and 1 to 2 is 3 from here. So we're comparing this to the to 2 plus 3. So we're comparing infinity to 5. And which one is smaller? 5 is smaller. So we update that piece right there. Does that make sense? So this says to get from 4 to 2, we can't get there directly in one move, right, with no intermediate vertices. But with one intermediate vertex where we're allowed to go through vertex 1, you can get from 4 to 1 in 2 moves, and from 1 to 2 in 3, or distance of 3, not 2 moves, but distance of 2 and distance of 3. So that distance is 5, and 5 is less than infinity, so we're going to update the 5. Okay, now we're going to do the same thing. We're looking at 4 to 3, but we're allowed to go through 1. So what happens to 4 to 1 over here? That was a 2. And 1 to 3 over here is 8. And 2 plus 8 is 10. But the label that we already had was -5, and -5 is smaller, so we keep it. And now we're looking at 4 to 5, which before was infinity. But again, we're going to look at 4 to 1, which was 2, and 1 to 5 is -4. And we said the minimum, and what is infinity? Well, infinity is definitely bigger than -2. So we're going to replace that with -2. Now, what do we also have to do? We had to check everything else in the whole matrix in the same way. But that's the only row that gets updated this time. You can check that if you don't trust me. Does it make sense? So what does this have? This has the shortest paths that start at a vertex and use vertex 1 or not, right? But don't use any other intermediate vertices. Right? Use 1 or not, but nothing else. So now we're going to do the same thing with 2. Do we need this matrix anymore?
No.
We don't need this one anymore. We just need that one. Right? Because now any lookups that we do, we're just going to look up there. Because now what are we considering? Now we're allowing I to j, and we're allowed to go through 1 or 2, or you can go straight there still, right? And straight there, we've already recorded that information is in our numbers. So you're allowed to go straight through if you don't have any intermediate vertices at all. All right. So what happens here? We do the same kind of thing. Let's take a look at going from, again, all of these are zeros. Let's go from 1 to 2. 1 to 2, and you're allowed to use 1 or 2 in the intermediate, so nothing changes. Let's go 1 to 3. We're looking at 1 to 3. So 1 to 3 right now is 8.
What? You get there with 7.
Sorry?
You get there with 7. A total of 7, like 1 to 2 and 2 to 3.
Oh, okay. Yeah. So now we're going to consider 1 to 2 and 2 to 3.
Although we can't go to 2 to 3.
So what is 1 to 2? 1 to 2 is 3. 2 to 3 is infinity.
Tough.
And so what happens? The 8 doesn't get changed.
The arrow part was hiding behind 2 circles.
Was it this part?
Yeah. There we go.
So that one doesn't get changed yet. All right, let's look at 1 to 4. 1 to 4 is infinite right now. But what are we allowed to do? We're allowed to look at 1 to 2 and 2 to 4. So let's see what happens on that. 1 to 4 doesn't help, so now we're including this other possibility, 1 to 2, 2 to 4. 1 to 2, we look that up and get 3. 2 to 4, we look up and get 1. So what do we replace the infinity with? A 4. And then we do the same thing for 5. 1 to 5, distance was -4. So now we're looking at 1 to 4, or 1 to 2 and 2 to 5. 3, 2 to 5 was 7, and we're comparing -4 and 10, so no changes to the -4. All right, and we just do this again and again and again, all through here to see if there's any updates that happen. If any updates happen, we make those changes, and we can throw away that matrix, and we have this one. And then we go on to D3, which means now we're allowing what? We're looking from I to J, and we're allowed to go through 1, 2, or 3, or none of them. We can still include the possibility of having gone directly from 1 to J. So what happens each time? We've solved an optimal subproblem, and then we don't have to solve it again. We know the shortest path from this point to that point. And then if we ever need to use that path again, we have the answers. We just look up the shortest distance. Update things for D3. Update things for D4. Where do we stop? What's our last matrix?
K equals N.
Yeah, we stop here because at this point, all the intermediate vertices are 1, 2, 3, 4, and 5, which is everything. And so we will have updated everything with the best answer, the shortest distances for any path that we look at. What if there's still an infinity left? You just can't get from that point to the other point, right?
Would that mean it's disconnected?
Well, you might be able to get there one direction and not the other direction. So with directed graphs, you have a different issue. The underlying graph might be connected, but it might not be connected in terms of the directions that you're allowed to go. And so what happens here, we have at the end then a table that tells us the shortest distance from 3 to 4 and the shortest distance from 4 to 3, right, when you get done. And they might not be the same answer because getting from 3 to 4 might be shorter or longer, right, a lesser cost or a higher cost than it would be to go the other direction. But we'll have the table with that information all in it. So what does it come down to? It comes down to cycling through all of the pieces and looking at the previous table to see, okay, what happens if you add these two numbers together? Is that less than the entry that's already there? If so, I'm going to update this. If not, I'm going to keep the old value. What does this algorithm not tell us? It doesn't give us the actual path. Right? It gives us the cost of the path. So what could we do to get the actual path? Just like we did with our modification of Dijkstra, we could keep track of this in a separate, in this case, a separate matrix that would incorporate what the intermediate vertices included. So we can have a series of matrices that we're building as well. And then, like we said, wherever it was, back here, we can then use that extra information to actually compute an optimal solution. Here is the path, if you needed to do that. But if the only purpose is to calculate the shortest distance, then we don't keep track of the extra information. But if so, we can just keep track of it as we're computing. We can't reconstruct it after the fact, though, right? You have to keep track of it whilst the process is ongoing.
Are there any complications that come up in Floyd-Warshall? Like our A star had like the memory issue.
Nope. It's a matrix, and all you have to keep track of are two matrices. So the downside is, the worst thing is that if these are really, really big, you just have a lot of data to keep track of.
Did you ever have any problems with like runtime?
No, runtime is just the order cubed, right? Theta of the order cubed. So, the downside is if you had 100,000 vertices, then this matrix is big, right?
Gotcha.
So that's the issue in that case. There's a lot to keep track of if we're trying to do it by hand. But otherwise, if we're not trying to do it by hand, if we code this, it really is that, then it's just doing lookups, right? Comparing values. Look this up, look that up. Okay, which is smaller? Smaller one, make the update, otherwise don't. And we do have to be careful that we're not making the changes in there at the time. Right? We do need the extra copy, because in a different row we might need the information before as well, but we need the old information, not the new updated information. Right? So we do need to keep this matrix until we've built this one, and then we can throw that one away. And we'll use this one to build the next one. And then so really, what are we doing? We're recursively finding the shortest paths, but as we break it down to find the path to get to that point, and the path to get to the point before that, and the point before that, and so on, we don't solve it in that order. We solve it from the small case, the starting point, solve it up, and record the information as we're solving it. And then other times when we would have to solve that same subproblem, we just look up what we already calculated and put that into place. All right. So on the last lab, we get a chance to implement A star, and with this a value that we can toggle on or off for Dijkstra, right? Set the heuristic to be 0, and Floyd-Warshall.